I think I'm plugged in, yeah? No, we don't need that.
Don't stop. Right.
It's good to work on hard builds. Right.
Oh, I'm sorry.
Simple buildings are the hardest. Okay, that was
We'll have everything in there.
Okay. So lastly today, I just wanted to introduce you guys quickly to flow design. To get a feel for how to use it, and more importantly, how to understand the information that it's giving you, right? We've talked about this a little bit, previously about how to understand airflow around buildings as it relates to load shedding specifically, and what it is that, again, you're looking for in terms of the analysis. Also, this can help you understand a bit better how you might be setting up, problematic areas at the ground level as well. If you're seeing high velocities of wind, I've got a little chart I'll show you in a minute, that if you're setting that up at the ground level, you might be making it uncomfortable for pedestrians potentially if it's getting really high, those velocities. So I'm going to actually show you two ways to use flow design today. The way I typically have used it is flow design. It'll either plug into Revit or work as a standalone. If you use it, I always use it as a standalone because you can get more. You have more parameters to play with, and you're outside of the Revit environment, so you don't have all of the other processes taxing the machine as well. And in fact, this is the first time I tried doing it on a laptop today, running it on a laptop today. And it's extremely slow on the laptop. I have a big workstation that I'm typically working on when I'm doing the CFD. It's very computationally intensive and a lot of video card actually activity. So it's a little bit difficult on the laptop, but I'll show you the basics. Working both in Revit to sort of get an understanding about how you can quickly look at a few things in Revit, but then also how you can take your model from Revit into flow design and get some better results. The visualization capabilities within Revit are very limited, and so you can only kind of look at it in one way. All right. So what I have right now, obviously, is some just real basic conceptual masses. One sort of like your Shanghai Tower, right? So you can see the differences between the two geometries, and the other is a pretty typical square tower. So if you've loaded flow design, you have the flow design tab up here, and you simply just click on that, and you'll see that you have a start button here. Again, because flow design is so computationally intensive, it will not allow you to have any other windows open at all while you're running it. So once you hit start, you're in the flow design analytical model, right? And so as you can see, there's a sort of there's a default condition that you're going to start with. Pretty clearly, the wind is coming from one direction here and moving across our conceptual masses, and it's simulating what the wake is. Now it's set to 3D simulation right now. I'm going to put it on 2D simulation just quickly. The 2D simulation is going to calculate much faster. It's only calculating the information in that one plane, right? And you can see the differences when I go to 2D simulation because it's calculating at a much better rate. You can see the differences here between the, actually these masses are not being read properly at all. It's actually just blowing right through this for some reason. I don't know why it's doing that. Maybe it's in that. Where was it where you could change the analyticals? Properties. Select on it. Yeah. I think it's gonna. I don't think it's. I don't either.
I wonder if that mass is open.
It might. Potentially it is. Anyway, this one looks like it's responding properly, but this one is not. I don't know why that is, actually. I'd have to go into it a little bit further. But at any rate, you can see, I'll keep going through with Revit right now just to show you how you change the parameters here, and maybe that'll affect some things. Usually, the way I work is you have a 2D simulation operating at the beginning of your session because it will calculate faster and you can start to set up your bounding geometries as you're going, right? So this box that is shown up here is the solution space, and again you can kind of see that, is the solution space for the test, right? Right now we've got a lot of area that is being calculated that we may not need. So you can adjust these the solution space volume, and that's simply by clicking on the tunnel size box. The interface for this is a little clumsy. It's better in the real flow design. I don't know why it changes so much, but as you slide these sliders around, you can see what's happening with the bounding box. The smaller the bounding box, the less computation is required, because really what the CFD analysis needs to fill the volume of the box with air, essentially, and it does that by populating the box full of a three-dimensional array of pixels. But these pixels have information embedded in them, and so they actually call them voxels. Anyway, it's got to fill the entire volume so that it can understand how the air is bouncing off itself and off other things. Which is why it's so computationally intense. So, I probably went a little bit too small because the edge of the box is obviously interfering with the flow around this building now. So I'm not getting an accurate result because of that. Out here, you can kind of see that the flow breaks to something a little bit more consistent, but again, I don't know how it's reading this geometry. It doesn't look like it's reading it properly. So this bounding box is a little bit small for what I'm trying to test, so I'm going to slide that back out. Hopefully, wrong one. Just to enclose a little bit more area. And then you can do the same thing on the top and bottom as well. So if we, right now our top is way higher than we need, so we can slide that down probably to about here. But again, we need a bit, oops, did I just cancel it? Again, we have to have enough space that allows for those. Allows for those voxels to, resolve to undifferentiated or disrupted airflow, right? So we're going to that point. Now, if this is working properly, the way that this wake should work is it should be flipping back and forth much more aggressively than this one, which is unfortunate that we don't see that, but maybe we will when we go to the actual flow design. Also, just very quickly, here you have, I don't know why the text isn't showing up, but it's not. Here's where you change your wind direction within Revit, this is radically different than the way it works within flow design. So obviously, as you look at your windrows, you can sort of populate your airflow based on the way the windrows looks in your your research. So depending on which direction the airflow is coming from, you can just slide this around, and it'll change the direction that the airflow is moving through the solution space. Right? Pretty straightforward. So, and you can also see, quickly that, just by changing it, we get a different profile, wake profile behind this geometry. Depending on how it's reacting to the geometry at that space, which is pretty quick, pretty easy to see. Again, I wish this was working properly, because what you want, if you're concerned with load shedding, the thing that you want, what you're looking for behind your building is a consistent wake, right? You don't want it moving, flopping back and forth. That's representing turbulence, and turbulence is where you start to get load building up on the sides of the building, which, obviously in order to resist that, you have to stiffen your structure, add mass, add material, etc. So that'll show you your wind direction, wind speed, pretty clear too. This again, you can get this information from your windrows as you move out concentrically in your windrows. It should tell you what the wind speeds are, and I think probably in miles per hour. You need to convert that to feet per second, so you can understand, or so you can input the data correctly. Because obviously, if I ramp this up pretty high, it changes. I mean, it doesn't look like it's that much different, but you can tell that the wake field moves radically differently at low speeds versus high speeds, right? And again, you want to put this somewhere close to where your prevailing winds are typically, and then you can go from there. Okay, so that gives us, sort of setting up the environment that you're working with. Now I haven't hit right now this solution that we're developing right now is only being calculated in this plane. So it's not a very accurate solution at all, because it's not responding to any of the voxels that may be generating vertical turbulence, right? But I'm not going to go to the 3D simulation yet, because I want to show you how to move this plane around first. So, as we're, I think it's one of these guys, yeah. So here we have our plane position. So it tells you exactly the height that you're cutting your plane through, which will be useful for understanding the relationship to surrounding buildings, pedestrian height, etc. That's pretty straightforward, right? You just flip it around and it shows you what's going on differently at the different levels. Okay, and that's one of these guys. You can also look, and this is more important for maybe lower buildings, is the orientation, where the plane is cut. You just select your plane position and then select the plane that you want to look at, and it's going to change the profile. Now, of course, I've got to move this so it's actually intersecting some geometry. Oops, wrong one. There we go. So now you can see, and this is actually good. This is a good representation of the difference between a 2D calculation and a 3D. Because in the 2D calculation, what you're seeing here is that we're generating a lot of high-speed winds across the top, all the way out to here, and this is a giant negative pressure, and if you could see the vectors, which you can't visualize in Revit, which is unfortunate, you would see that there's a big vortex being generated here in a 2D plane. Okay? Okay, but if we change this to a 3D simulation, it is now going to be calculating the entire volume of our solution space, right? And so now the entire volume is being calculated, and you can see how different the representational plane is at this point for the way the air is actually moving. And this is more accurate in terms of how the building is actually going to be performing. So again, but you can see it's going, the calculation is pretty slow, and you'll probably hear this thing start to sound like a jet. And you're not seeing the real turbulence right now, just because of how intensive it is. But you can record, render your results, and you'll see that a little bit better. But more importantly, it'll start to give you some basic information that you can work with your conceptual mass before you move it into flow design itself. Which is what I would recommend, because it's a lighter program. It doesn't have, obviously it doesn't have all the other components with Revit running as well. But this gives you, again, a way that, especially as you start detailing this model, and you have curtain walls, etc., you can get in there and start looking at the way the curtain wall articulations are affecting the airflow in different ways, especially if you're thinking about passively conditioning your building, and how you might be bringing air through the facade at local moments. Revit is a little bit better, or is a good way of understanding it. But again, unfortunately, and you'll see the differences in a minute, the only way you can visualize things within the Revit environment is through the color gradients. And it doesn't even give you a scale, which is unfortunate as well, unless you start to insert these nodes. But I haven't got them to work yet today, so I don't know why this instance of flow design isn't quite responding well. You're supposed to be able to add these probes into your airflow, and it'll give you the actual results of the data at that point, like what the airspeed is, what the direction is, etc. But I can't get them to work in this instance for some reason. But we can do that over in flow design. So, but again, there's a little bit of see what happens when I throw it over this box over here. You can see any difference. Yeah, it looks like it's reading it a little better. That's about what it should look like. With a box geometry, you get a profile characteristic more like that. Okay, but I really want to look at these within the flow design standalone. Flow design as a standalone won't read a Revit model. Only Revit reads Revit models. So we have to export this thing, this geometry, so that we can open it within the flow design software. So before I can do that, I have to finish out the flow design simulation, and that takes me back to the Revit environment, right? And at this point, we need to export this geometry for flow design. So go up into the export tab, and you want to export it as an SAT file. That's the one that I've had the best results with in terms of exporting from Revit. If you're going from Rhino, there are other alright, well, hopefully that works. Lady. Okay. Alright, so when you first open Flow Design, you're going to get this window, you know, pretty typical. These demonstration models are exactly that. They're already modeled instances that you can play around with. What we want to do is import a local file, and I'm going to do the CFD test. Hopefully it works. Okay, cool. Got some geometry. Alright, so this environment is much more robust in terms of visualizing what's actually happening. Alright. So, but again, we have to understand the parameters of the solution space that we're working in, right? Then this is, once you're in flow design, it's actually pretty intuitive. You know, the tabs across the top are pretty well laid out, and they again sort of explain exactly what it is you're looking for. just go through your simulation settings, your resolution. The resolution is super important if you are trying to understand the way the airflow is working, at lower levels. To begin with, I would leave it lower and faster with your, at 100%. You'll see what that means. But really, this is the data that you're looking for on the right side. And specifically, the voxel size at 12 meters right now. What that means is the solution space is a 12 meter, the smallest resolution is a 12 meter size space, which is huge. So our accuracy isn't going to be great at this point, right? It's going to give us some good initial understandings of what's going on, but once we get those understandings, then we can crank up the resolution to see what it's really looking like. Again, that's going to take a lot of computational power, so you want to wait until you're ready to do that after you have the rest of the model set up. All right. So I'm not going to mess with that yet. The wind tunnel. This is where we're setting our solution space again, right? So you'll see the interface is quite a bit different now than it was in Revit, with the exception of you have your familiar little guy over here, your navigation cube, which within the flow design space you're going to use a lot, because the way the flow design navigation works, it's not geared towards architecture where there's a gravity and a clear bottom. It's built for product design, and so in product design you're flipping all over the place and orientation doesn't matter that much, so it's really easy to get lost in your model, and so you'll be hitting the navigation cube quite a bit. Anyway, this is more of a visual setup. You can see what's happening on the upper right side. The dimensions are changing. Again, you want to try and get yourself into a position where you're not totally calculating a lot of area that isn't necessary, but you need enough so that the boundaries of your solution space aren't interfering or aren't fully resolving to undisturbed area or wind. Obviously your wind speeds here are now in meters per second. That's because the simulation is in metric. You can change it to inches and English, or I would probably leave this. I'm going to leave the model dimensions at millimeters because that's the way it brought in, but display in English. So now we'll get our English units, which is a little bit easier to understand. Now you understand how big that voxel size is. It's huge. But that's setting up our solution space, and you'll see it'll calculate a little faster now with the smaller solution space. And again, as soon as I start navigating, I get flipped all over the place. Oh, of course, right now it defaulted it to 3D again. I'll go back to 2D really quickly. This is the 2D solution space, and you'll see the massive difference. You'll see how this, when you're only calculating the 2D, you get that massive vortex, but really, in reality, you're not going to get that. And of course, the way the display is working now is we're looking at the streams of arrows, and this is much more useful in terms of understanding how we're disturbing the air, because what we're looking for, at least in load shedding, I'll talk about insulation or trying to pull air in for passive conditioning, we actually want something different. But for right now, if we're looking at load shedding, what we want are streams of air that are parallel, or more or less parallel, right? So that's laminar flow. And laminar flow will not induce that turbulence that generates load on the building, right? So right now this building is in the wake of this building, so it's probably getting helped a little. But what we should see, the difference between these two, is that we should see some curling starting to happen behind this building. which is indicative of that, if I can get over there, yeah, which is indicative of that turbulence that's generating on the back side of this building. Again, I think it's getting helped out from being in the wind shadow of this building, but you can see them starting up a little bit, and I have the resolution kind of low anyway right now. But before we get into more specifics, different ways you can visualize in this program, within the program itself, is either through flow lines or planes of gradient, just like we were looking at before. Again, I'm getting lost. So we can see those gradient colors, but now we have a key off to the side over here that tells us exactly what's going on. So where we have the bluer colors, we have a lot of stagnant air, right? And that's again because we're kind of, even though this plane, this is also a good representation, even though this plane is just barely cutting through the model, or not even cutting through the model, it's being affected by the airflow that's being kicked out around the model. So you're seeing what that's looking like in this plane because it's a three-dimensional solution space, right? It's a good way to visualize it. So we're getting a lot of stagnant air. If I move this out a little bit, you'll probably see a range of high-speed air somewhere closer. It's not allowing me to move it very easily. Anyway, mostly at the top is where you're getting the higher speed. Again, it's a lot easier to move things around in this one. You just grab the handle and move it, which is good. Pretty easy. There's one other visualization that's pretty interesting, which is called the Isosurface, which is this. And the Isosurface shows you all of the air that is at a defined airspeed, right? The way you understand that is you go into settings. So right now, this isosurface is representing all the air that's at 31.4 feet per second, and we can sort of make that more transparent, and we can kind of see what that looks like. What's interesting about this is you can start to see how the air in front of the building is sort of stacking up as it's moving into the building. All right. What's that? As the air is coming in, the building is large enough that it can't move around fast enough, so it starts to build up on itself. And so you get this zone out here that sort of stacks up on itself. At this airspeed is not bad. You'll see if I flip to the, you'll see what the impact is if I flip this real quick. If I go back to plane and we look at it, from the top, drag this down. Crash. I probably should close Revit actually. What's that? Yeah, when you're first, especially when you're first sort of designing the project, all you want are the skins. You don't want to load down all the geometry because it will try and read that extra geometry, even though it's not going to be used in the model. But yeah, keep the model as clean, as simple as possible at first until you start getting into, and again, we can talk about it. As we start looking at environmental systems. You may want to draw air into your building through the top of the floor slab or the bottom and set up circulations. At that point, we want to look at room level flow, and you'll probably just bring a chunk of your model in at that point. Yeah. This program will give you a decent understanding of what's happening. Yeah, decent. It's not going to be great. There's another software that is free for you guys also. It's called Simulation CFD. And an Autodesk product, and that one is the one where you can really get high-level calculations of airflow because it takes into account temperature as well, which is really important when you're talking about that. Exactly, and so that package will take into account buoyancy, for instance, and how that's going to develop circulation differently than just the difference in pressures. That's getting pretty sophisticated. Also, like if you put a body in the model, it'll radiate the heat from the body and start to understand how convection is set up through that too. But that one's it's a beast, that program. But it's pretty good. This will give you a good initial sort of intuitive, not intuitive, a little better than intuitive, but it'll give you a good initial understanding of how the air is circulating, right? But of course you have to be smart in how you set up your model. You can't enclose the space, and you may want, that where the intake is and the output needs to be set up so that you actually set up, you build the negative pressures with your solution space appropriately. It's a little more difficult to do it in this to get a good result out of it, but it can be done. And the way to do it is to leave the back of the room open. Don't put a wall there, and you can simulate it in this program. But this is more for looking at this case scenario. So I actually, before this thing crashes again, let me try and get that. Doesn't like the laptops I found. So the question was, how did I get the longer flow lines so you could see what's going on? Every time you change this, the view analysis, the next two boxes change a little bit, right? So with flow lines, you get a settings box, and that pops up, and this is where you set the length of your flow lines. I had already had it previously set to 500, so they were really long. I think the default is pretty short, something like that, but it's a little easier to see if they're longer, obviously. And I also have the size pretty small so that they don't look gigantic, right? That's not really useful in the understanding it. I also have them going fast so I can see the turbulence going on. But actually 1,000 is a pretty low count at this point. You can see I can really bump this up, and it gets totally, you can see it start to build, and you can't even see what's going on in there. But you can start to see the way the turbulence is building up a little bit. But I did want to show you the plane view from the top real quick first, with that question. So even though we saw the isosurface was building out way up to here, there's really not a big drastic gradient difference from the front of the tower back. So it's going to feel pretty comfortable in the way that it operates. So you get right up to it, and that's where you start to get a low flow developing. Now there are two things I will show you. One thing that's a little confusing about flow design, because it was designed initially for product design, is the way you change the orientation of the wind moving across your objects, right? Revit understands that you're an architect and the building is stationary, and so the wind direction moves around your building, right? In this instance, because this is for automobile design, for boat design, for whatever objects, like transportation industries, the flow isn't the wind or the environment isn't the primary driver or the primary variable in terms of that flow, but rather it's the velocity or the vector of movement, right, that creates that airflow. So the way that you move your model or change your wind direction is you actually have to rotate your model, right? And this gives you all 3 degrees of rotation, again, because, in product design, you're all 3. The z-axis is what we're concerned with. And what you'll see is as I slide this around, the models spin, right? And that just rotates the space of the model in the space of the solutions set. So I'm going to make it 90 degrees so that they're side by side rather than lined up in the airflow, right? And so the box, our solution space is always, there's always an inlet and an outlet in that box, and it's always on the inlet's on the, if you look at it from the top, it's from the left, and the outlet's on the right. And now the box isn't so great in relationship to these guys. I'm going to slide this out a little. Still, that box isn't reading very well. I wonder if that surface is inverted or something. It's not bad though. That's looking a little better. So you can, slide up and down and see what's going on. Okay, so one of the things that we're going to want to be, the ways you're going to look at your model most, though, in order for us to understand what's happening is through the, I haven't talked about surface pressure yet, but I will in a sec, is through the flow lines. Again, the flow lines, what you're looking for, when you're dealing with load shedding, you want parallel lines. When you're trying to set up stagnant zones, you want to see some curlicues starting to develop, which you can kind of see in there. But they're hard to see, right? Because there's so many other lines around here. So in the visualization of this, one of the things that you can set up or change, we have our solution space, but in our settings here for the flow lines that we were just in, where you can set the count, speed, direction, you also have a seed box manipulator. So when I adjust this, I don't change the solution space, but I do change which of those arrows are being displayed, right? The velocity arrows. So now I've changed I've changed this to only display those streams that are within that other box, right? So you can start to see what's happening. Well, I think I shortened them a little bit too much again. It just flipped all over on me. Yeah, I moved it a little too far. Let me slide back out this tad. So now we can start to see what's happening behind the building proper without having to try and look through all of those other layers. Like, we can't really see what's going on back there on that one. And so we start to get a little bit of a visualization of what's happening here. Starting to run out of time here. Okay, one of the things that isn't, that would be affecting our model right now is there's no ground plane. The ground plane is super important when you're understanding a building, because that ground plane is going to create drag leading up to the building as well. I forgot to throw the ground in this model, so right now we don't have a ground plane in here. But again, you'll want to have a ground plane in your model because that ground will create drag. It'll change the profile as you move vertically. And in fact, and now I'll go to some of these. Wait, not what I wanted. Yeah, this one. So these are some diagrams. You can go to, this is just the help on the flow design, and it sort of outlines areas that you want to look for that are problematic in building design, right? Where you have these accelerations and canyons and around buildings, those are places that might end up being uncomfortable. You have these large, unstable pockets that typically happen behind rectilinear geometries. That's where that corner chamfering comes in that I was talking about the other day. Just simply addressing the corners of the buildings, you can develop a wake field that is more stable and doesn't develop these large pockets like that. And then, it gives you a nice little chart about what's comfortable. I thought it was going to show the wind profile. It doesn't, though. I'm going to open Revit back up real quick. This is the one thing that Revit has that Flow Design doesn't have. Because, again, Revit understands that architects are working with it. I'm going to open up this guy. In lieu of having to build a ground plane when you're working in Revit, they've built in a velocity profile, or a wind profile chart, which I can't quite get to. Just lost it. My screen real estate isn't big enough for me to get to it, apparently. Yeah, it's right underneath the wind speed. You have a wind profile. And what it is this allows you to define what your wind profile is as it addresses the building. And the way that a building typically looks, and I don't know why. Oh, there we go. The profile, and I'm just going to sketch it really quickly. You can look it up. But the way the wind profile typically looks is something like that, where at the ground it's really near zero, and as you go up, this should be up higher. I don't know why we're at negative. No wind below the ground. Won't let me get off of that. That's weird. Huh. Anyway, it should be up here. It's really interesting that they have it at negative. Yeah, that might be it. Yeah, there you go, thanks. Can't see the entire box. Maybe the model is, I think this Chris, is this model 4,000 feet below sea level? Well, anyway, your profile as it hits the tower should be something like this. And again, you can look it up to get the exact curve. But what this will do is it simulates that drag along the ground before it hits the building. Something like that. And if I could get down there to hit apply, which I don't think I'm going to be able to, I would. Ah, there you go. Thanks. Alright, let's close it. You'll see that you saw it really quickly there. It changed the way that the profile, the wake profile was generated, because it's again changing the velocities according to that curve. Simulating the ground drag that's built in. So I think this will be, you should all throw your geometry into Flow Design, get some, save some views of it, and sort of start talking about where, or trying to understand how the airflow, the geometry is affecting the airflow around it. And then as we go into the post Autodesk week, we can look at, hopefully we'll understand a little bit how you can manipulate the geometry within the airflow to get some feedback as you're developing it. The biggest issues, the biggest takeaways from this are mostly that you need to understand how you're setting up the solution space. That's a big factor. And then, I didn't get back to that over here, but once you have something that is working pretty well, at least within the flow design environment, you can step up your resolution. And as you step up your resolution, you'll see the voxel size will shift, hopefully. And also, if you shrink your solution space, that'll help your voxel size as well. So I got it. It's maybe 2/3 the size. When you're starting the question about moving through the room, in order to get accurate results of the airflow in the room, your voxel size really needs to be somewhere around 1/2 inch, so that you're getting a good representation of what the airflow is. I don't know if you can do that on a laptop though. It's pretty high resolution. Even this might crash the machine at this point. So towers. So one of the towers from Darts. That's what I use at home. Basically, is the Mac Pro tower. It can handle it. All the simulations I showed earlier in the semester were generated on that. Half of them were done in flow design, and half of them were done in the CFD simulation CFD, where buoyancy and everything is taken into account. Yeah, got something. Now I gotta change the stream size. It's too small. Any other questions? Okay.
So, 3 things for one today. 5 stories within an analytical model through your mock-up tower design. And then 2 more installs need to happen in here. The robot that we're going to be using right away on Wednesday. So I think because you guys all stay with these stations, come back to these same stations at some point before Wednesday at 2 o'clock and get robot installed. It's going to take a little bit longer, but it's the same process that we just did with flow. And then the dynamo install that we'll need to do as well, I will post on the Moodle so that you're sure to get the correct version. And I'll send an email just to confirm that. But those 3 things you'll need to get done before 2 o'clock.
That's pretty good.
Yeah, so remember you'll need your model for DSI on Tuesday morning, right away when you get back. To jump into the SARI with.
Yeah. So actually, now that I've bumped up the voxel size, you're seeing a better airflow around this tower. It's re-laminating. That was the principle of this geometry, right? One of the principles of this geometry is that it would shed load by laminating the air back together as it moved around it. You can see that happening here. And then hopefully when I slide over to this guy, it'll be slightly different. In that it should, if I can get got lucky and got a good spot. Yeah, and it's actually okay. It's not terrible actually right there. Should be worse than that. They are terrible. But you can see it's actually pulling in pretty tight back behind it, unlike this guy, if you were to compare the two. But the resolution needs to be a little bit higher so that you get a little more of that going on. The voxel size is in the wind tunnel settings. Oh, no, sorry. In the simulation settings. Here you have simulation resolution. I've got it at 300%. If you make this, every time I've tried 500%, it's crashed. Oh, yeah. How do I save the video?